Rightio. Okay. Reflection, diffraction, refraction. Okie dokie? Yeah? Continue? Yeah. So, oh, my bullet points disappeared. Well, still, quite a lot. Quite a lot. Okay, so let's start with the easy one first. Reflection. I think you all know this word, but how can we give a definition to reflection when we're talking about waves? So, Lynn, do you want to give it a try?
So when the light crossing through the material,
Yeah, go on, yeah.
The way of the light
Yeah.
is bending.
Oh, close, close. I wouldn't say bend, but you're kind of getting the idea. Anyone else?
It's like symmetrically or perpendicularly bounced.
Not necessarily perpendicular.
Not at the same angle.
Not necessarily at the same angle. So reflection is the change of direction of a wave at a boundary between two different media so that the wave moves back into the medium it came from. So I'll give you an example before you write that down, okay? Let's say here, well, I'll draw it in a little, I'll draw it from the top. So here you are looking at a mirror. And that is one medium. And here you are in the room, which is full of air, and that's a different medium. Okay? And maybe you have a little, let's say a little flashlight or something like this. So you're holding a little flashlight here. So the wave is in the air. It tries to enter the second medium, which is glass, but it can't enter this shiny glass, can it? What happens to the light? It moves back to the medium it came from. Okay? Now, think about it. If I look at the window, the light can move through the window. It can move from this medium into the glass, and then from the glass into a new medium again. Okay? Or sometimes the light can be blocked, for example, with the wall. The light comes out, and what happens? It hits the wall. Well, it reflects too. You know. So, I know what you guys were thinking, that the light comes in at one angle and comes back out at the same angle, or something like this, but it doesn't have to, because if the mirror was bent, then they will go in many different directions, but it's still reflected. Okay, so the key thing about reflection is that it comes back to the medium it came from. You're not happy with this, Zach?
What if there's no medium?
How would it? Oh, okay. So here, medium could be vacuum. Because funny enough, we don't really distinguish so much between air and a vacuum. Even though for humans the distinction is important, for light it's not so much. Okay, so you need this definition for reflection. Okay, you got that? You got that? Yeah. Common examples include the reflection of light against a mirror, sound in water against a wall. Reflection. Okay, next one. Diffraction. Anybody know what that one is? Yeah. Say again? Say again, Zach, I just didn't hear you.
It's altering the wavelength, the frequency. Or splitting into its components. Yeah.
No, it's... Do you think you know?
When you move into a different medium and
No, diffraction.
Isn't that
oh,
when
that's
it
refraction.
gets
So what's
dissipated?
different?
No, it's
Yeah.
ends.
Dissipated. Occurs when waves bend around small obstacles or when waves spread out after they pass through small openings. For example, here, if you have a very small gap and the wave passes through the small gap, the wave then spreads out. If the gap is quite big, then doesn't spread out as much. This is diffraction.
We study the Doppler effect.
We don't, unfortunately.
It's not.
This is the change of frequency caused when the source is moving.
Oh.
Yeah, yeah.
So that basically happens with all the speakers.
It's like when you have ambulance.
An ambulance. Yeah. Also occurs with the redshift of light from
Yeah.
stars. Yeah, if you can add the picture too, that would be great. Okie dokie, you got that?
Few seconds.
Got that? Diego?
Almost.
What are you doing? Oh, you don't need me to keep the image up to draw waves coming out. You know where they go. Alright.
Yeah, but
Now, the last one, refraction. Does anyone know refraction?
that's what nothing passes through.
No.
No, it's the one I was talking about when you enter another medium.
What happens?
Oh, yeah, yeah.
The
It's like with rainbows.
The angle, yeah.
They get, yeah.
Yeah.
They get
it
bent.
gets,
The angle changes.
yeah.
So, refraction is the change in direction of a wave caused by the change in the wave's speed. Refraction is seen most often when a wave passes from one medium to a different medium. And here is an example. asking me?
Usually, if it's, how can it happen when it's not in a different medium?
Let me think about that. I don't know, but I'm sure there must be some situation. Yes, I'm sure there must be some situation to make the wave change its speed without having to change the medium. No, maybe not. I'll have to Google that later. I'll see if there's any situation.
Does it get affected by heat or anything like that?
Yeah,
Like
that's kind of affecting the medium though.
Oh,
But it would affect it for some waves.
I guess like, you know, in hot rooms where they kind of just bend the images.
Yeah, but you can kind of technically think of that as two mediums, the hot air and the cold air. So, all right, you got that? You got that, guys? Yeah? Okay. Now, some materials will allow light to pass through it more freely than others. Obviously, glass lets the light through easily, wood does not. But some materials are even better. So like glass maybe is better than water for allowing the light to pass through it. You know? And what I mean by allowing it to pass through, I mean allowing it to pass through at its normal speed. Because what happens is, that speed I gave you, 3 times 10 to the 8, that's only in a vacuum. It'll just be slower in other materials. Some materials will slow the light down. For example, light moves slower in glass than air. So we need a way to measure this effect. And we use something called the Refractive Index N of a material. Is a measure of how fast yellow light can travel through the material. Mathematically, the formula is quite simple. It's simply C over V, where C is the speed of light and V is the speed of light in that material. So, will this N be more than or less than 1? Or more than? Which is bigger, the V or the C?
The C.
Yeah, so
More than
more than 1. Yeah. In fact, N is between 1 and infinity. What is the situation when N equals 1?
that
Like-
means it's just
It's in a vacuum. And what is the situation when N equals infinity? It means the light has stopped moving. Yeah. Is that possible? Not really. As far as I know, the material that can slow the light down the most can take it from its speed of 3 times 10 to the 8 and slow it down to a speed of 1 meter per second. That material has the highest refractive index. I can't remember the name of it. It's a material constructed in the lab. But you can slow light down so much you can see it moving through the material at 1 meter per second. Yeah? So if the V is 1 meter per second, then it means the N is 3 times 10 to the 8.
Why is it yellow light?
It's just part of the definition because you'll have to specify some light as a benchmark. Do you know what I mean? Zach, it's a bit like in chemistry where you have standard temperature and pressure. Do you know?
Like all electromagnetic radiation moves the same.
No, I thought that too, but the refractive index depends not only on the material but the type of the wavelength of the electromagnetic wave as well. So when you say, oh, this has a refractive index of 2, you actually only mean for yellow light it has 2. It moves half the speed. Okay, is that okay, guys? Yeah? Does anybody know what it is for glass? Or water? For water, does anyone know what it is for water? It's about 1.33. So, you know, that means the light is going about 30-something% slower. Yeah? Continue? Now, we have this law called Snell's law, which is useful for refraction. And one way to state Snell's law for calculating the angles is sine theta 1 over sine theta 2 equals n2 over n1. Now, I need to explain the angles and the ends here. So, this is material 1. This is material 2. Theta 1, I'm sorry if you can see it, this is theta 1 here. This is theta 2. This is n1 and this is n2. Okay? Now notice please that you measure the angle not with the boundary, but instead with the perpendicular normal. Okay? So for example, if I have light coming down to the table, I don't measure the angle with the table, I measure it instead with the perpendicular line. Be careful with that. Also be careful that it's 1, 2, but 2, 1 here. You can imagine a common mistake being 1, 2, 1, 2. Okay. Now when you write this down, listen. You don't need to write all of this down, okay? It's enough if you draw this picture or something like it. Okay? So if you can make note of Snell's law. And this will be one of the experiments we'll do. Yeah.
That's what we have to do.
Measure the angles. Yeah, the boxes in the other room. You might want to note actually that sometimes theta 1 is written as I and sometimes theta 2 is written as or. Do you know what the I and or might stand for? Incoming is fine for I, but I think the technical word is incidence. But incoming is like this. And the or, well, I'll give you, yeah, refracted, yeah. Man, I'm getting hungry. Been teaching since 9. Connell and Colin are on my case to get the corrections done. Like, dude, I'm busy. Your exams!
Oh, they're
You remember?
corrections.
Remember the exams you did?
I thought they were finished, correct?
Ah,
I don't want to see them.
Then you're meeting tomorrow.
I'll have to get them finished this week. Or next week. And the problem is I'm teaching intake 2 as well, you know.
Yeah, now you're busy.
Busy. Ugh. And I have to correct your essays as well. And then you'll have your maths coursework soon for Joan, won't you?
Oh, no, for Fiona.
Alright.
2 weeks.
Yeah. You got it on Monday?
Yesterday.
Yeah, yesterday.
Oh, today's only Tuesday. Oh, right. I thought we were longer in the week. Alright, do you have that? Do you have that? Yeah. Now, under certain conditions, it is possible to choose an angle for theta 1 so that theta 2 is 90. And this angle is called the critical angle. Let me show you. Listening to music? Yeah. So let's say this is N1 and this is N2, and there's the normal. Okay, the light comes in at one angle and then goes out at another angle, theta 2 and theta 1. What we would like to do is, can we choose an angle here that will make the light move along the boundary? And the answer is we could. Let's see what the formula says. So Snell said that would be sine theta 1, which I'm going to call C, over sine 90. That should equal, which is 1, which is N2 over N1. So that means C, what's called the critical angle, will equal sine inverse N2 over N1. And what will happen is, if your angle is bigger than C, it'll actually come back. However, this is not always possible because you need N2 over N1 to be less than 1, because you can't get sine inverse of a number more than 1. So this is only possible if N2 is smaller than N1. If that is the case, it's possible to find a critical angle that will make the wave not enter the next medium. And this is called the critical angle. So, the critical angle is blah, 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 blah. And I have some pictures here. Now, actually, I need to talk a little bit more about this. But before I do, I think this bit here might be good to write down if you want to add this to your notes. And I need to talk more about it. This is called the critical angle. The critical angel is what kills you in a boss fight.
Bring that Dark Souls. Andrew is A-N-G-E-L.
Yeah.
Ah.
Yeah. Now, the other word you need to have here, can you see, sorry? If you're at the critical angle, you move along the boundary. If you're more than the critical angle, it actually comes back to you. So it's like a reflection now. And we call this situation here total internal, do we call it a reflection? No, total internal refraction. Is this situation when your theta 1 is more than your critical angle. Yeah. This total internal refraction is, I believe, how your fiber optic cables work.
Oh, yeah.
Yeah. The light keeps bouncing between the glass internally. Okay, you got that? Right here. So to have a critical angle, you need to go from a high index to a low index. Okay, you got that? Now, look, this is how you usually think about it, but in real life, it's a little bit messier than this, which is what I want to show you next. Okay. So you have this formula here for the critical angle, but I want to talk about these three pictures here a little bit. So this situation, when the eye is less than the critical angle, then the light comes in the high index medium and out the low index medium. But actually in real life, if you did this, you discover, strangely, some of the light actually comes back in. The light splits. So in my diagram, I didn't include, for simplicity, I didn't include this. My picture was like that, okay? Then in the next picture, when you're at the critical angle, what did I say happens? The light comes in and then goes along the boundary. But again, strangely, some of the light splits and comes back anyways. And then finally, in the total internal case, when your angle is bigger than the critical, then it all comes back in. So even when you don't have total internal, you still have partial internal. When you're at the critical angle, I would say about half the light actually comes back in anyways, at the critical angle. And here, I don't know what proportion, but when you're less than the critical angle, still some light totally comes back in. Now, I think this is not super important for the exam, although I have seen it come up once. They had some question like, it was kind of a little unfair, I thought. They had some question like this where they said, the light is at its critical angle. Calculate the angle the light comes back in at. Because, the question said something like, when light is shown at the critical angle, some of it will travel along the boundary and some of it will reflect back in. What is the angle it comes back in at? It's the same as critical angle. So it was kind of a sneaky way to ask, what's the critical angle? You know? So like I said, I've only seen this come up in the exam once. It's not a big deal, but if you can copy this into your notebook. Now, what I would like, if you could, try to make these both faint, because this one is darker than these two, because the light is being split. Okay? Yeah?
Why does that happen?
I don't know. But you can see it happen when you do the experiment.
Okay.
Yeah.
Is it because of the surface, it's not super smooth, so there is
No,
something?
I don't know. I just know that there is a tendency for light to split when it travels through semi-reflective materials like water or silver or things like this. You know, it is maybe to do with the fact that water or whatever the medium is partially reflective. You know, you can kind of see a reflection in it when you look into water. The light doesn't 100% go through. So my best guess is that because it's partially a reflective material, it's not 100% reflective like a mirror.
Itself is not completely.
What's that?
The material itself is not completely stationary.
That's another factor too.
Yeah,
But I think it's more to do with the fact that it's partially reflective anyways.
But then, if it wasn't super smooth, then the angle wouldn't be the same as the critical angle.
Oh,
It would be a different one.
the non-stationary feature will make the light wave wobble in its angle. We'll see all of this when we do the experiments. Yeah. So I think that's why the last one is called total internal refraction, because in the other two situations you get a partial internal refraction. Do you know what I mean?
So the last one should be just the same.
The last one is exactly how I drew it earlier here, Dorian, when it comes in, it tries to leave and comes back in.
So it's not split at all.
There's no splitting in the last situation.
So those N2 is all smaller than N1.
It has to be for these to happen. You can't have a critical angle.
Yeah.
Okay, can we continue? Still more to do. Right. Notice in the last lesson you did not see white light listed, did you? The frequency and the wavelength of white light. That's because there's no frequency for it. Why? What is white light?
It's a mix of three.
It's a mix of all the colours, yeah. So we have a frequency for red, orange, green, etc., but none for white. White light is a mixture of all the colours.
Snell.
Yeah?
White LED. What does it emit? What type of?
White LEDs aren't 100% pure white. There's a little bit of blue in it. So it's a mix of most of the colours, but I think blue is a bit more dominant than the other colours. I think. I'm not 100% sure, but it's not actually white.
So it's more
Really,
white.
yeah. Really, the only true source of white light is the sun. But even that is not 100% white. It has all the colours except for 2 shades of red. Yeah, I mean, it has 99.999% of the colours you might need, but technically there are 2 shades missing from the spectrum. Yeah. But it's the closest thing to white light, anyways. Okay, so white light is a mixture of all the colours. That is, when red, orange, etc., are mixed together, you get white. There's nothing to write down. I think you might have known this point anyways. So what gives below? If you look at this picture here, according to Snell's formula earlier, you have this. If you remember Snell's earlier, sine theta 1 over sine theta 2 equals n2 over n1. Okay, what is the n1 here? It's the air. Or, well, the air here. And what's the n2? The glass. Or if you look here and here, what's the n1? The glass. And what's the n2? It's the air. Okay. Is theta 1 the same? Yes. Is theta 2 the same? No. You have different theta 2's, don't you? But why? Because this is the same, this is the same, and this is the same, so shouldn't this be the same? Well, no. One of these 3 things is not the same. Does anyone know what it might be?
Because n is 0.
Oh, because the angle they come in.
No, they're all coming in at the same theta 1.
Yeah, they are. Each of them is vibrating in a different.
No. And 1 doesn't change.
The speed, because
It's the n2. Remember the definition I gave you for n. It's only for yellow light. So only the yellow one is actually obeying Snell's law. Now, it's not that the others don't obey Snell's law. It's just that they will need a different n2. Okay? So the n2 for the red light is actually a different constant than the n2 for the yellow light. And this is why the colours split. Because the n is different for each colour. Okay? So that's what's happening here. The n changes for different colour. In fact, the n depends on f. Now, I'm not sure if that's right, if I meant to say n depends on lambda, the wavelength. Maybe.
Because it depends on the speed of the light.
Yeah, maybe. Maybe it is the f. Or whatever. It depends on the colour, that's for sure. It's practically, I know, Dorian, it's practically the same, but it's technically one of the 2. I'll have to check which. Anyways, I'm just mentioning this as a reminder that the formula is only for yellow light, but in the exam whatever colour they give you, they'll give you the N for that colour. You know, so if they give you red light, then they'll tell you the N for red light. Okay, so it's not to worry. Right, there are other ways that Snell's law can be stated. So we gave you one way to state it, but there are other ways to state it. You can also state it as sine theta 1 over sine theta 2 equals lambda 1 over lambda 2. The wavelength changes. So, I'll give you an example here. Let's say we have our air here and glass here. And let's say I have, there's the normal. Let's say I have some red light. And this red light will have a wavelength, lambda 1. Now, it'll come out here. Oh, sorry. It'll come out here. And it will have a different wavelength, lambda 2. Now that's interesting because you might think, oh, so if the wavelength is different, doesn't that mean the colour changes? Because remember we said different wavelengths mean different colours and so on. Do you remember that? So technically what's happening here, is the colour depends on the frequency, not the wavelength. So here this has a frequency f1, and here this has a frequency of f2. And f1 will still equal f2. And it's the frequency that makes the colour, not the actual wavelength. Okay? But do you recall the formula C equals lambda f? You might say, well, hang on a second. If the f is the same, shouldn't the lambda be the same? No, because when is this formula only used? In a vacuum. And are we in a vacuum here? No. So that's why we're allowed to have a different wavelength but the same frequency. Because we're not in a vacuum anymore. Okay? Now, I think this situation is actually important enough for you to draw. The frequency stays the same, but the wavelengths differ. However, the colour stays the same. So if it's red here, it still comes out as red here. Yeah. Now, why does the frequency stay the same? Well, what does the frequency represent? It actually represents the energy. Remember we said high frequency means high energy, like gamma and so on. So what rule in physics is making the frequency the same? Conservation of energy. The energy in the light is going to stay the same on each medium. Now, I don't think it'll be exactly the same. I mean, the glass will probably be warmed a little bit by the light. So maybe in real life the frequency drops slightly.
Why do you call it, if it's technically the same, why do we call it F1 and F2?
Oh, just to distinguish the frequency in the first medium and the frequency in the second medium. You're thinking deeply about this, Zach. What are you thinking? Have I broken your brain? Something I said doesn't compute?
I'm just thinking
Why what?
why astronauts in a vacuum, if they were to turn on a torch, they would be propelled in one direction.
Ah, that will come up in quantum mechanics later. Light, believe it or not, actually has a small momentum. So it's actually the conservation of momentum that is what you're talking about there. But we haven't discussed that yet. That's in the final chapter. Okay, can I continue?
So it's lambda 1 over lambda 2.
Oh yeah, I'll go back to the formulas in a moment. Yeah, it's 1 over 2, not 2 over 1. Huh?
How does it have momentum if there's no mass?
Again? Quantum mechanics? We'll see.
At the end of the semester.
That's it. That's it.
The best part for you.
Yes, indeed. NASA have worked on building solar sails.
Yeah.
Yeah.
Yeah,
Oh, yeah.
yeah. And it works because the light has a momentum. Just like
Huge.
air has a momentum, you know. But the momentum is so small that the sails have to be, you know, kilometre big to capture it, you know.
Yeah, I remember we had text in one of the exams. On
Did you? On solar
Yeah,
wind?
they wanted to, with one of the small
Microchips.
microchip thing.
Oh, with a giant sail.
Yeah.
Yeah. Okay. There's another way to represent Snell's law. That is sine theta 1 over sine theta 2 equals V1 over V2.
How come it's 1 over 2 and not 3?
Yeah, let me show you the proof actually. It's not that difficult. So, if you watch, sine theta 1 over sine theta 2 equals N2 over N1. That's Snell's original law. But if you remember the definition of N2, that would be C over V, in this case V2, and C over V, in this case V1. The C's cancel, and you're left with V1 over V2. Alternatively, if I want to introduce the lambdas, how do I do that now? If I multiply this by F1 and this by F2, I'm allowed to do this because the F's are the same. They cancel. No, I did that wrong, didn't I? V equals, yeah, sorry. I need to divide it, isn't it? F1 and F2, is that right? V equals lambda F. Yeah. So on the top, I'll get lambda 1 over lambda 2. Right, so they are the three forms of Snell's formula. Please take care with the 1s and the 2s. If you can write that down.
1, 1, 1, 1, 1. I'll write from. Jeez.
You just be careful. Just be careful with it, okay?
Do they give us this one?
I think only the first one. I think. I'm not even sure of that. Let's check the formula book. Okay. You got that? Yeah. Continue? Yeah. So, one use of Snell's law is in a lens. When light enters a glass lens, it will refract, but the lens is curved. This will result in different values of theta 1 and theta 2. However, the lens is carefully made so that the refraction will cause the light to converge. Now, what I'll do, I'll explain this with my attempt at drawing the lens. My goodness. Okay.
Lens and no eye.
Yeah. It's already gone pear-shaped. Okay. Now look. Imagine the light comes straight in. That's the normal, so it'll come straight out. So that's not so interesting. Oh, sorry. No, I mean to say it'll pass straight through. Sorry. It will pass straight through, like that. Okay. Now, the light will come in here. What's theta 1? Well, if you draw the normal here, this is theta 1. Okay? So it will come, I'm going to, okay. Stuff happens in between, but I don't care about that, alright? I'm just going to jump to the exit. So it'll come out, and it will have a particular angle here, theta 2. Now, what you can do is you can get the curve. If you can get the curve in the right shape, it means you can make the theta 2 such that for this theta 1, it will exit at an angle to meet up with other light rays. So, maybe for example, the light that comes here, it will need to leave at an angle of, let's say, 40 degrees. So maybe, for example, you need the angle here to be 30 degrees. So if you can curve it the right way, you can make all the angles such that the light will meet at one point. Now, the question is, what shape do you make this? Well, you can calculate what shape that is. It's quite complicated to calculate. Can't even remember the name of the shape, but it's a special shape that will make this effect happen. Now, you don't really need to know about that. You just need to know that one application of Snell's law is making a lens. That's one application. So in the exam, if they say for 1 mark, what is one use of Snell's law or refraction? One use of refraction is it can make a lens. Okay. So what I'd like you to do is, you can just write that sentence down. One application of Snell's law is in making lenses. We don't actually talk about concave and convex lenses. We just talk about lens, and that's it. We don't discuss it anymore.
But you have to know that one of them concentrates on the other.
Yeah, no, we don't even need to know that. I don't think so. I think the syllabus is just like discuss an application of Snell's law in lenses or something like that. So we've discussed it. But there's no requirement to, students need to know the laws of lenses, like focal point and all this type of stuff. There's no need for that. Okay, continuing. Now, before I do this example, I actually want to skip that. I'll come back to it in a minute and talk about this. Can we demonstrate this? Can we describe an experiment that shows the reflection, diffraction, and refraction of visible light, microwaves, and water waves? Now look, I'm going to show you how to do it for light. It works the same way for the others. You just have to maybe change the equipment. So the first one, how could we have an experiment to show that light reflects? So we'll do the first one, a reflection experiment. Reflection of light. How could we demonstrate this? Well, I think we need, number one, a light source. So we need equipment, light source. What else might we need? Mirror.
The smoke.
No, I think that's about it. A mirror. Oh, let's make it a little bit fancier. And then let's say some paper. And then we can put the paper here and we can see, ooh, the light reflects onto the paper. Or maybe actually we'll even say we'll use a laser, a little laser pointer.
Yeah, that's what I was thinking. You put the smoke and you see actually.
Oh, okay. Yeah, no, let's not get too fancy now. All right. So I'll let you write this down in a minute, but maybe we can talk about the next experiment. So that's experiment 1. No, not for this. No, this experiment is only to demonstrate the phenomenon, the effect. You don't need me to write a description of this, do you? Surely not. You can write your own description.
Yep.
Point the laser at the mirror. Observe the laser reflected onto the paper. End experiment. Yeah. Right, number 2. How might we demonstrate diffraction? Well, again, you need the same equipment, but you also need you'll need a diffraction grate. Yeah. So what you have is you have this little grate, okay, and again you have your light source, your laser, and your laser comes in, and what happens? You put your paper here. and I think
See it bigger.
you can see it bigger. What you could then do in the description is you can say in the description to move this, and you should see this getting bigger and smaller. You can do the same thing with the water. You know, you can have the water pass through the gap, and you can extend or contract the tank, and you can see the water spreading out more or less, you know. Or you could even, actually what you could, well, maybe not the diffract, you could have multiple diffraction grates, maybe 4 of them, of different widths, and you could see the different diffraction. So what happens if you use the smaller width? You get some more, yeah. Again, you don't need me to write this description, do you? You should be able to write this yourself, I
How
hope.
would you reflect microwaves because you can't see them?
Well,
How
no.
do you measure them?
You just need, so I said paper. So replace paper with microwave wave detector, right? And then replace mirror with material that reflects microwaves, you know? Where can you get a material that reflects microwaves?
Glass of your microwave.
Exactly, just tear the door off the microwave oven. Because that material is designed to reflect the microwave back into the microwave oven.
How do you actually work?
But how do you observe when it's reflected?
Well, it's like I said to Zach, instead of having a piece of paper, have something designed to detect it.
Okay.
You know? Now, perhaps you can get something like some material like a Polaroid, something like Polaroid, you know these materials? They react to different frequencies. For example, an X-ray. An X-ray is the Polaroid is specially made to react to the X-ray coming out of the equipment, you know. I'm sure you could go to even eBay and find a material that will react to the microwave. You know, maybe it'll change colour when it's struck by the microwave, or something like this. The last one is refraction. Well, that's the easiest one. What's the only other thing you would need? You would also need a prism. That's this glass here. Okay? And once again, you have your light, it shines through, and then you'll observe it comes out at a different angle. And then you've demonstrated refraction. Yeah?
What happens when you put lasers to a prism?
To the prism,
Yeah.
it just refracts.
But does it split?
No, because it's only one colour. I don't know what you need to write down. I think these experiments are fairly obvious and straightforward. Don't write down what I wrote. Write down something better. So if you can make some note of this. Oh, you don't look happy. It's because I'm making you use your own words. Do you want me to write something? Now, after you write this down, what I'm thinking is, given how big this lesson was, and given how many questions there are, I'm thinking about, and also given how small the wave chapter is, because you can see there's only 5 topics in it, I'm thinking of making the next physics a double tutorial where we work on these wave questions in class, and any problems I can do them on the board. Okay? Because obviously the last 2 topics aren't so important for the exam, you know, but the next one is a big topic for the exam. We want to make sure we can do them. And some of them get very hard, especially the older ones. You wrote something down for these, Zach, or just drew pictures?
I remember.
Will you?
Yeah.
Will you?
I will.
We'll see.
It's quite straightforward, as you say yourself.
What are you going to use as the reflective material for the microwave?
Tear off the microwave.
That's it, good. What are you going to use for reflective material for the water?
For water. Reflective.
Reflective material for what?
Yeah. Yeah, a wall. Yeah, a wall. Yeah,
This comes back and then
Yeah, yeah.
comes out.
just a wall. Alright, you have this, Lynn? Yeah? Alright, well, we'll wrap it up there. Oh, you have a tutorial now, don't you? In what room?
This one.
This room? Okay. Now, do I want a burrito or do I want a shawarma?
Shawarma all the way.
I'm thinking about two, Diego. I'm thinking it's a shawarma day.
It's good, you know, the weather's not so.
Yeah, no, that's what I'm thinking too. That's what I'm thinking.
Have to do it for an hour.
What's wrong with you? You have to wait an hour.
Until we can eat.
Did you have breakfast?
Yeah.
Okay. What did you have for breakfast?
What about second breakfast?
Second breakfast. I didn't know you were a hobbit. Right. Have you got that? Can I close it? Well, what did you have for first breakfast?
Cereal.
Cereal's not so filling.